All right, in this video, we're going to talk about gases and the ideal gas law. Before we do that, though, let's talk about circles really quickly. So if I draw a circle, it doesn't matter if it's a small circle or a medium circle or a big circle. We know that's kind of the same size. There's a property about circles that states if you take their diameter, d, and they all have different diameters, and you also measure their circumference, right, so their area around the edge of the circle, they all have different circumferences. And if you take their circumference divided by diameter for any circle, you always get the same number, 3.141592, yeah, we call it pi. And this is a constant for all circles. Doesn't matter what the circle is, what size, circumference divided by diameter is always pi. And so the reason I bring that up is because when we talk about gases, if I have a container of a gas, there are four variables we can measure about the gas. One of them is temperature. It's pretty straightforward. We know temperature is a measure of average kinetic energy, basically how much energy the gas has. Volume, how much space the gas takes up, typically in liters. So liters. Temperature we're going to measure in Kelvin because Kelvin's an absolute scale, meaning 0 is the bottom, so we want that. We can also measure N, which is how many moles of gas are inside the container. So that's important to know. And the last thing we can measure about a gas is P, pressure, which we're going to measure in atmospheres. At sea level, pressure of the atmosphere is 1 atmosphere. That's what that means. So if I have a gas in a container, if I measure those four variables at these in these units, Kelvin, liters, moles, and atmospheres, it turns out that the pressure times the volume divided by the moles times the temperature for any ideal gas, and we'll get into that at some point, what that is. But PV over NT will always equal the same constant, 0.0821 liter times atmospheres over moles times Kelvin. Now, the reason this has units is unlike with the circle where you're dividing a distance by a distance, so the units would cancel. Here, these all had units to start and they just don't cancel. So this constant has units, and like we called the 3.14 pi, we're going to call this R. So R is the ideal gas constant, equals this, and it's P times V over NT equals this. So that is sort of where this comes from. Now, what that allows you to do is if you have any container of gas, doesn't matter what it is, and you know there's four variables here. If you have a container and you know 3 out of 4, so you have P, V, N, and T, you can use this equation, which is typically shortened to PV equals nRT. If you know 3 out of 4 of these variables, you can always solve for the fourth. And I have a separate video doing those, so if you check that out, but this is just the general idea. You can solve for these things. So that's the ideal gas law. That's what this is useful for. Now, there's other gas laws that come from the ideal gas law, which we're going to look at in a minute. But before we do, let's look at a quick simulation here. So here is a container. I'm going to pump some gas in here. And notice there's temperature, there's pressure, and there's also this is a rigid container, so it's not changing volume. And so a few things you'll notice. One is what happens to the gas when you start heating it up? So you're giving it more energy. And not surprisingly, the particles are moving faster, the pressure increases. This pressure is basically a measure of how many collisions and how forceful the collisions are on the wall. So if the gas is moving faster, we expect the pressure to go up. If it's moving slower, if we cool it down, we expect the pressure to go down, and it eventually will. If we get it cold enough, if we could somehow get it to so they're not moving at all, 0 Kelvin, then theoretically the pressure would be 0. That is why, that's what absolute zero is. That's how it was first theorized, basically a linear extrapolation of how pressure changed with temperature. All right, some other things though. Let's say we heat this back up a little bit and the gas is at a certain pressure. Let's say I take this container and I shrink it. Well, now the gas has less room, there's going to be more collisions, the pressure goes up. If I make the container bigger, now there's more room and the pressure goes down. So we can kind of see how those all play out. So there's all these relationships between pressure, temperature, and volume, which if you think about what would happen, sort of makes sense. Another thing is if I start pumping more gas in here, we also expect the pressure to go up because there's more stuff in there. So all these variables relate in that sort of way. And so that allows us then to go back to, let's say we have two gases. So we have a gas and a container. and then we change something about the container. So let's say that I have container 1 and container 2. And actually, it's really the same container. Let's say that the gas was at a certain pressure, call it P1, a certain volume, V1, and a certain temperature, T1. And there's also a certain number of moles in there. I'll call that N1. So if I take this container and I change something about it, let's say it's the same container, and maybe I just expanded it, maybe I stretched it out. Well, now there's going to be a new pressure, P2. There's going to be a new volume, V2, a new temperature, T2, and a new amount of moles, N2. Typically, we say no gas gets in or out, so oftentimes N1 equals N2, and so we never really make much consideration of that. So here's the point. We know that P times V over N times T equals R for both of these containers. That is what the ideal gas law says. So if that's true, then the pressure of this container times the volume of this container times the moles of this container times the temperature of this container, divided by that, is this P2 V2 over N2 T2, these both equal R. So we can actually set these equal to each other. And as I said, typically when we do this, we say N1 and N2 are equal, so they will cancel out of this equation if they're equal. Well, not out of this equation, sorry. When I set these equal to each other. So I can set P1 V1 over N1 T1 equal to P2 V2 over N2 T2, because by definition, both of these things both equal R, so they must equal each other. And then once I set up this equation, if N1 and N2 are the same, they will cancel out. This is known as the combined gas law. And again, I have another video that goes through how to do math problems with this. I just want you to understand the origin story of the combined gas law. In addition, if anything else is the same, if this container is at the same temperature, if both these at the same temperature, then T will cancel out. And you'll get another gas law, which is just a simpler version of that. So anyway, this is where it comes from. I guess theoretically, you don't need to totally know where it comes from to solve with it, but I just wanted to sort of explain that. Also, very quickly about what an ideal gas is. There are two requirements for an ideal gas. The first requirement is that there are no IMFs between molecules. So the idea is that we don't want the gases to stick together. So what kinds of gases are more likely to be ideal? Ones that don't have strong IMFs. So nonpolar substances are good, things like that. Also, as the gas gets colder, they're more likely to stick together because they're getting closer to becoming a liquid. So the hotter the gas is, the better they'll be at not interacting with each other. So that's one condition. The other condition is that the gas particles themselves are considered to be very small in comparison to the size of the container. In other words, they're not bumping into each other because they're just really big gas particles and like they're having trouble. Like if you're in a crowded room, you might have trouble getting through the room because you take up space and so you're pushing through. Whereas if you existed as a pinpoint, you could probably get through even if it were crowded. So we have to assume that these gas particles are pretty small in relation to the size of the container, which means that as they get too packed together, they start to become less ideal. This is a little bit more than you probably need to know for this unit, but just that's the basics of what makes an ideal gas. So anyway, that pretty much sums things up, and just we'll go from there. So until next time, I am Derek Genova. Have a delightful day.